Thank you, Thomas. Thank you, Sven, for having me. It's actually going to be a joint presentation by NUMECA and Friendship System. Using fine marine with CAESES via intuitive modeling on the basis of radial basis functions. That's what we announced for the NUMECA SMM-CFD workshop for today. And just before Christmas, we were approached by a joint customer, by Yachtwerft Meyer, and they asked us if we could do a catamaran optimization on their behalf together. It's an electric catamaran ferry that they have a bid on. And we said, okay, yeah, let's give it a try. And if we can make it in time, we can also present it here at the workshop. And this is what actually happened. So it's a joint presentation by Sven Albert, who will take the second part, by myself. I'm going to have the first part of the presentation. And we, of course, like to honor the contribution by Massimo Kovacic, the guy from Yachtwerft Meyer. Now, what is the design task? It's a catamaran. I will briefly discuss that. I will introduce Yachtwerft Meyer, and for the sake of completeness, ourselves. NUMECA, I don't think we need to introduce in this workshop. Then I will cover parametric modeling. I will give you an overview of the workflow. I will discuss radial basis function as used here. And then Sven will take over and give you the insight about the hydrodynamic optimization. And then, of course, we will have some concluding remarks. There's an electric catamaran ferry to transfer between two ports on a rather short leg. It's a bit less than 1 sea mile. It's, as you can see, a pretty small vessel, 11.5 meters in length. There are two distinguished displacements, one with crew only 14 tons. And if it's fully loaded with around 60 passengers, it goes down to 21 tons. On the major leg between the two ports, it's traveling at 7 knots. That's a pretty high fruit number for a standard vessel, 0.35. And in the port itself, it goes at low speed. We did an energy consumption analysis and realized that at high speed of 7 knots, most of the battery power, because it's an electric powered boat, is used on the major leg. So we said we can safely assume that if we cover the two displacements, we will get the majority of energy consumption if we concentrate on the 7 knots. And the aim, of course, is to reduce energy consumption at design speed so that we can either gain distance covered with a single battery charge or go slightly faster if need be. The partners working together, I already said, it's Yachtwerft Meyer from Bremen. They do tenders for yachts and super yachts and for cruise ships. They do composite models for various vessels, and they do special crafts for the Bundespolizei, for instance, but also for offshore supply and offshore support vessels, and for passenger ferries, as we are discussing today. Friendship Systems, the company that I work for, we are a long-term partner of the NUMECA Engineer Bureau. Thomas, in his presentation this morning, when he talked about the Riva, already mentioned us. Our main software that we develop and license is CAESES. We just came out with CAESES 5 in January, and actually CAESES 5 is also used for this catamaran example. We are a natural partner to NUMECA because we don't do CFD, but we do geometric modeling as needed for simulation-driven design. That is, the variation of the geometry that we can offer is robust, so that we can, for instance, always deliver a watertight and really a nice geometry in the simulation-driven design process. The simulation-driven design process itself entails, as you have already come to know, several components: variable geometry, pre-processing. This is what CAESES does. Then fine marine takes over with grid generation and the flow solution. And then, for instance, fine design is run to actually look into variations and to discuss what are the best variants. Now, in the context of this presentation, I will focus on one particular type of variable geometry that we offer within CAESES 5. We actually have all those as a toolbox available, but we will only talk about radial basis functions today. This is a fairly new functionality that we offer. It belongs to partially parametric modeling. The Riva example that Thomas discussed this morning is a fully parametric model realized within CAESES, but we will focus on the radial basis functions. What are radial basis functions? Basically, it's a morphing principle that we apply here. And I'll show you an example for the catamaran on the upper part of this presentation, and for a totally different type of vessel on the lower right part. And you see that a factor is changing between more or less 0 and 1. And this is what happens. We morph between one geometry and another geometry. And the one geometry, the baseline, we use as a source, and the geometry that we want to go to, we use as the target. And the morphing is, so to say, realized by switching between, so to say, the two, between the baseline, the source, and the target. And there are two ways to run this. We can either use the factor between source and target, or we can change the target. Those are two types that we offer within CAESES 5 and the BRAP morphing functionality. For the CAT simulation and optimization that we are presenting here today, we actually used that we kept the factor between the two, the source and the target constant, but we changed the target itself. And this is shown here in the lower part of the animation. Now, how do radial basis function work? Some math, but not too much. It's basically a vector field that we build up so that each point in that vector field in the domain, any point on the geometry, is receiving a displacement in delta x, delta y, delta z if we are in a Cartesian coordinate system. You forget about the details. Just look at the right side of the presentation here. The red dots are fixed points. You can think of them as, so to say, a clamped support. So anything that is shown here in gray, that is, so to say, embedded in these red points, is kept. It's not changed. But anything that is shown in dark green, that's to be changed. And let us take a look at the sources. For instance, a part of the designed waterline for this catamaran that we want to optimize, it's shown here in red. They are also fixed. And now we can introduce the target, namely, here shown in the green line, a change of the designed waterline. And the targets and the sources and the fixed points go into a large matrix that's be solved, and that gives us the radial basis functions that we need to give a displacement to the baseline. Okay, now that we have an understanding of how the actual flow geometric variation takes place, let's take a look at the workflow for the electric CAT. We started with importing a baseline. We actually used an IGES geometry file. Then we prepared the baseline, added trends in the deck, set up the RBF. Then we start to apply the changes to the baseline, make variations according to the three variables. We have attached a fully parametric stack for the bare hull. I'll mention that briefly in a few seconds from now. Then we merge the current variant with the flow domain, which is then being exported and handed over to Fine Marine. It's a multi-body STL file that we hand over so that colors and everything is there, so that Fine Marine can nicely use that in a batch mode. Then Fine Marine is set up for the investigation. We then run a design of experiments. This is similar to what Thomas already explained in the Riva example. And then on the basis of that, optimizations are done and undertaken. And then, of course, you discuss results within the partnership and repeat the loop a few times. How much time have we spent on this? Now, Jakob Meyer actually approached us just before Christmas. Not the ideal timing to start a project. So we said, okay, if you work on your baseline within Christmas and New Year's, we can then start the whole process of optimization early in January. That's what we did. Jakob Meyer handed over the first baseline early in January. We then spent one day setting up and fine-tuning the RBFs. The next day on the parametric stack model. Then NUMECA Engineer Bureau took over. They produced very fast, very quickly the first CFD runs, did checks and quality assurances. That all in all took a day. and an extra day for streamlining the optimization process. And then we just sort of say went for the number crunching, no interaction needed anymore. And then, of course, we met a few times for about an hour in virtual meetings. Well, in these times, we cannot meet physically anyway, and discussed the intermediate results and the final results. So this is what Jagd Meyer gave to us. We then added transom and deck. We defined the sources. You can see there are sources for the designed waterline, for the stem contour, for the aft body of the center plane curve. There are controls, points, curves. You could also use surfaces to define sources. And then we use those sources to represent them as targets, and then we modify the targets. So in red, you see the sources, not that many, a few points, a few lines. And these are the targets in green. So the geometry, the new geometry, as realized through the RBF modification of the baseline, then complies to the targets, and we can then start doing variations. A quick word on adding the SCAC to the bear hull. This is a fully parametric model, as said. So it's simply merged to that bear hull, and if it's changing the bear hull, I'll show that in a second, that will follow. Okay, let's take a quick look at three variables that are used for the optimization. The entrance angle, for instance, at the design waterline is to be changed. I'm always showing min and max values so that you would get an appreciation. We make and introduce an asymmetric part of the bow. You can sort of say, come from a symmetric Damai hull, it's a catamaran, to a asymmetric Damai hull. Then, of course, you want to change maybe the transom. You want to change transom angles. These are all now free variables that you nicely can introduce intuitively. This is where the title of the presentation comes from, by means of the RBF. And it doesn't take that long, I said, about a day to really set all this up and then be ready for the optimization. Now, let's take a quick look at a combination. What I just showed you was one free variable to be changed at any time. And now we have, of course, a combination. You can already see the catamaran itself. We suppressed the clearance of the Damai hulls so that you would get a better appreciation of the form variations that we can realize very intuitively with this RBF method, looking from below, looking from above. And of course, no one of us would know beforehand which is the best configuration for our particular design task. Take a look at the SCAC. The propeller position and the SCAC outline in the vicinity of the propeller bossing is not changed, but of course the parametric SCAC adapts to the bear hull as need be when it's varying. All right, so we have a nice parametric setup for our variations and can now hand over to NUMECA to fine marine and fine design. You would then basically tessellate the hull at a pre-described refinement level. You merge that still within CAESES to produce a domain. Let's sort of say take a look when we cut through the domain. So the domain actually has colors associated so that it can then be run in batch mode, and Hexpress will be able to identify the various parts for the grid generation. And with this, I'd like to hand over to Sven for the second part of our presentation. Sven.
Yes, Stefan, thank you. So there should be a seamless transition. Let me quickly give me my moderation rights. And yes, there we go. You should be seeing my screen now. And yeah, I'm bringing up the presentation exactly where you ended. So, hydrodynamic optimization. The model is ready. Parametrics are defined. Now it's time to do some number crunching. Before we do any optimization, it is obviously also always important to check a few things on the base design, and that's what we did here. So we did a few initial investigations. What about the vessel speed? We heard that 7 knots is the mostly used speed. It is around about 50% of the operating time. And our simulation showed that we get a drag of around about 3 kilonewtons for the whole thing. So all of the simulations that I will be showing are done in full scale. Then we have investigated another operating point, 3.5 knots, which might be during harbor entering or exiting, maneuvering, and so on. And we see that there's a huge difference, almost of one order of magnitude in the total drag, which then in the end obviously also means that the energy consumption at 7 knots during the lag mode, so to speak, is the dominant one. And another thing to check out was the displacement. This is a passenger vessel, and the values that we see here on the right side in the graph are given for 14 tons. That is basically the vessel plus a few men of crew. But it can also be fully loaded up to 21 tons. And you see here how the numbers compare. As expected, the drag will increase by quite a bit. We see again the same trend. 3.5 knots is far less important in terms of energy consumption compared to the 7 knots run. For the CFD setup itself, it was really straightforward, typical resistance applications. Stefan mentioned it. We were quite on a tight schedule here. But when we were provided with the initial geometry, we just put the CAESES on top of it, and like 1 hour later, 1.5 hours later, we had our next meeting, so to speak, the three of us, and we could already show some converging results using, of course, mesh and our CAESES. So as I said, it's a typical resistance application. We solve for the sinkage and trim. We apply our adaptive grid refinement for the free surface entirely, so there's no more pre-refinement in the mesher around the free surface. That is done completely in the flow solver. And putting all these things together, we decided to go for the 7 knots operating speeds or speed, but using two displacements, 14 tons and 21 tons, because as I said, this is the one that is heavily relying on the battery, and will probably be around 80% of the total energy consumption when you make such a transfer from one island to the other. And of course, the objective was bring down those numbers, bring it down from 4.3 kilonewtons to, let's see how far we can get. Another thing to investigate always is grid independency, mesh density. We did a few variations on the mesh size. You can see here a mirror plane simulation on a 1 million cells mesh with a high Reynolds wall modeling. This is without the free surface, and here a comparison to a 400K cells mesh, and you see actually the difference in wave pattern is very, very small. And also when we looked at the resistance values, all of the resistance values that I will be showing are obviously averaged ones. So we take the last 20% of the interval and average it. So the difference in total resistance is quite small. Around 100K cells came on top to both of these meshes due to the AGR. And another thing, this is a catamaran, and the question quickly arose, can we actually do a symmetry plane simulation? Is that valid? So we made the comparison. We have here now the half model. The simulation is mirrored, but the domain is really half. And compare it to the full thing using the same mesh settings, of course. And you see there's some very, very little differences. And also when we compare the resistance values in our monitoring tools, the difference was, in this case, around about 2 newtons, which is quite negligible, we would say. Of course, these are perfect conditions for the catamaran. We go in calm water, we go fully straight ahead. It might be completely different in waves or when we have yaw angles and turning and whatever. But here we're going straight ahead, and we can definitely go for the half plane simulation. So that's our final CFD setup for the optimization. We go for a quite coarse mesh, around about 500K cells, and using half the domain. And yeah, next step is to set up the workflow, I will quickly go through that. So we have 4 basic steps in such a thing. We need to create a new geometry from CAESES here. We need to mesh it, solve it, and post-process it, get some nice pictures, get our integral quantities like the drags out of it. The transfer format here is STL, as Stefan mentioned, and on wrapping all around this thing is our optimizer Fine Design 3D, which uses a Python API to control all of the several sub-processes. The optimization strategy in itself, very briefly here, is based on database. So we have a random sampling of the design space which we opened. It was 10 free parameters. On that discrete set of data, we apply a meta model, and on that meta model, so the meta model gives a continuous description of the design space, and on that meta model we run the optimizer. In this case, we use a genetic algorithm. We run the simulation coming out of that design loop, put it back into the database, and then basically have a design iteration loop which will show some convergence at some point. Now, this is a meta model based optimizer, so it is very critical that we have a good prediction of the meta model in comparison to the CFD values. Here we achieved a very good correlation, so the points are very closely along that ideal line here given in black. Global correlation coefficient is 0.98. This is for one of the objectives, that's the resistance for 7 knots and 14 tons. And for 21 tons, we basically had a similar picture. Now the interesting part. The next slides will give you the total resistance at 21 tons, 7 knots over 14 tons, 7 knots. That was the 2 operating points we considered. And this is our entry point, the base design, around about 1600 kilonewton and 2250. Remember, this is the next slides are all going to be half model. This is exactly as the flow solver delivers the data. And this is our database. We ran 20 samples on it. We see a large variation in the drag values that we get. We also see a correlation of the drag values, which is not a surprise, because I mean they are more or less lining up along a diagonal. And the important thing probably is the best random sample in the database already showed a substantial improvement. You can see here at 14 tons, 39% drag reduction, and at 21 tons, 25%. And that was even without any optimizer run, which will be the next step. Our objective, as that, is to reduce the drag. Because of the axis convention, our best design space is going to be the top right part here. And the results look like this. So we have in blue our database samples. The cross indicates our reference sample, the starting point, and the yellow or orange points indicate the optimizer samples, so that have been found by the genetic algorithm. And this is now the design that we picked for the final round of evaluation. We could obviously have gone further, have investigated another set of objectives, but time was crucial here, so we were quite happy with the result that we saw here. And we see a drag reduction of 47% and 40% for the 2 operating conditions, which seems quite a good result. Now, these results are achieved on the 500K mesh, on a coarse mesh in mirror plane mode. So just to confirm all that stuff, we reran these 2 geometries, so the base design and the optimized design, on a full model without mirror plane, and also on a much finer mesh, 5 million cells. We also increased the grid density around the free surface by just specifying a parameter in the adaptive grid refinement. And we also switched to a low Reynolds model for the turbulence. And to fill it up, we also included another set of another displacement, 17.5 tons. And these are the results for the base design here, with the bottom 3 parts being 3.5 knots over the various displacements, and then the top 3 ones are 7 knots and the 3 displacements. And we are quite happy that we could confirm our trends in the optimizer. So we have in red the optimizer, the optimized sample, and in blue the base one. And we see the large gains we have seen in the optimizer run, also here in this final evaluation run. So it's for 7 knots, there's a huge reduction of drag and hence power saving. But we also see a very slight increase of the total drag for the low speed. There's 2 things to mention here. The operating profile is one thing. We did say the 7 knots run is the dominant one, so we only considered this. So anything about 3.5 knots is not gonna be is not known to the optimizer. So it's not his fault. We could probably redo the whole thing and say, okay, now we really want to include these points as well. It's just a new set of optimizations. We include a few more operating points, and we'll probably see a trade-off between these results. And now a few pictures, since we are talking CFD here. All of the pictures here are going to be taken from, or are taken from, the fine mesh, 5 million cells. Where do we achieve this increase, this decrease in drag? We have on the left side always the base design, 7 knots, 21 tons, and on the right side the optimized design. And we see quite clearly that the bow wave apparently is quite different, quite smaller, which in alone is likely causing a lot of this drag reduction. Another view from the bow here, again showing the large differences in bow wave build-up. And the side view, important because that was also something we discussed about the trim angle. We solved for the trim angle, and this could be kept. So both designs have a very, very small bow down tendency when they speed up, and this could also be kept, or was not worsened, let's put it like that, during our optimization. And this is basically a animation of this 5 million cells run comparing the 2 designs. So we see again the difference in bow wave, which makes probably most of the difference. But we also see, and that is quite important, I would say, a difference in the flow pattern, in the stability of the flow pattern here in the tunnel. The base design is quite fluctuating. There's unsteadiness observable in the flow field, while the optimized sample is quite stable. And this, I would say, also brings the drag down by some margin. So a few words, a few final slides on the geometrical part. I will quickly go through it because we are more or less running out of time here, but we have here now the baseline hull, and we're comparing it with the variant 15. That is the best one we saw in the database, and later on also the optimizer. So base design, bow view, compared to random sample, we see the asymmetry on the bow. We also see the decrease of beam width of that hull, and then the change from the random sample here to the optimizer sample, fine-tuning all of these parameters. The same goes for the stern. So coming here from the base design over to design number 15 from the database, and the final optimized design. And a side view and a bottom view giving you some impressions of the modifications that have occurred in this process. So to wrap things up, it was really an interesting thing to do, and also, especially also because of the tight schedule that we had, it was challenging. It was quite a challenging. I think the radial basis function we used or Stefan used in CAESES is really a big step forward because it is quite intuitive to use. You can start directly from a given geometry and don't have to do a full parametrization, which can in the end save a lot of time. We have proven quite a few times now the coupling is foolproof, so to speak. We use the colored STL files to share the geometry. Fine marine, yeah, we have found a quick setup. So so probably it was like 2 or 3 days of optimization and database time, so the number crunching, and therefore you need a stable setup and also a fast setup. And we found, again, given here, quite a few interesting samples, which show a drastic decrease in total drag, and again might be quite interesting for especially for electric propulsion, because here, as we know, energy is quite limited. So also thanks again to Yachtmaf Vaya for giving us the opportunity to show here, and thanks to Stefan, and thanks for your attention.
Thank you.
So let me quickly bring up the question panel if we do have something.
Okay,
yes,
I noted a few questions, and since you were speaking, let me take that over.
Okay.
I have a couple of questions to Stefan. Are there users who use workflows that tightly integrate NUMECA and CAESES?
Yes.
For example, doing the initial fairing with NUMECA and the classical, and then going on to CAESES.
Yeah, there are people that do that. Particularly when it comes to variation, you have the advantage within CAESES to build up your parametric model. So yeah, there are combinations.
Okay, and then questions regarding the RBFs. What if we would like to use potential flow methods instead of viscous methods? Then we have to work with surfaces instead of B-reps to create the penalization. Is there a possibility to use RBF in that context?
Yeah, no problem. That would be the same way to go forward.
And again to RBF, can the clamp location only keep a position, or can they also take care of a given tangent constraint?
The tangent constraint is actually taken into account. When you recall that picture where I explained the RBF, there were these red dots around the deck. And the number of those red dots are the points that are enforced to keep tangency between those areas that you modify and those areas that you keep. Of course, with a deck and freeboard joint, that's not important. But if you have, so to say, a smooth surface and you want to attach it, the modifications to that smooth surface, you would then use those points and introduce a tangency continuity.
Okay, thanks a lot. With that, I would like to hand over to Sven.
Yes. Are there any questions remaining? Probably not. So then it's finally time for a customer of ours presenting something. So Hauke, we are very glad that you made the time here. So Hauke is from Mecklenburger Metallguss, and he will give us some details on numerical propulsion simulation. So you are still muted, Hauke, and I will give you the moderator right now.